Variation and randomness are literally everywhere. Whether we're looking for a mechanical part failure, or determining a new drug's effectiveness, or even wondering if it'll rain tomorrow, most everything has variation. Now, one of the most commonly used statistical methods is ANOVA, short for analysis of variance. The whole purpose of analysis of variance is to break up the variation into component parts and then look at their significance. Let's motivate it with an example. Now, suppose we have 3 normal distributions, and the means are 0, 1, and 2. Now, they're different, but could they be statistically equivalent and fundamentally the same? That is, could they have all come from the same underlying population? Well, it's not likely. Notice that there's very little overlap among these 3 distributions. They have pretty tight variances. In fact, the means are more than 4 standard deviations away from each other. And we know that for normal distributions, just 3 standard deviations should contain over 99% of the data. Now, on the other hand, check out these 3 distributions. They have the same means at 0, 1, and 2, but they have a larger variance. In fact, it's more probable that these 3 samples could have come from the same underlying population. Now, if sample data were taken from the first 3 distributions, well, we would very likely find a statistically significant difference because the 3 distributions have so little overlap. But for the second 3 distributions, well, it would be much more difficult to find a statistically significant difference. They have significant overlap. Now, the reason they overlap is because of the higher variance. Remember, variance and standard deviation tell us about the spread of a distribution. So in order to test for a difference in the means, we have to analyze the overlap, the variance. Hence the name ANOVA, an acronym for analysis of variance. So the analysis of variance is commonly referred to as ANOVA, and it was first developed as an extension of the t-test, but with one very clear advantage. Now, ANOVA lets us compare more than 2 group means at the same time. Now notice I said compare group means. It may seem odd that we call a test of equality of means an analysis of variance. But as we saw in our example, determining whether or not the means come from the same population requires us to look at their variance. Now, ANOVA is used to model situations where our response variable is continuous and our variables explaining or predicting that response are all categorical. ANOVA answers this question: do categories have an effect? So, how is the effect different across categories? And is that effect even significant? Well, you can think of ANOVA as regression specifically for categorical predictor variables. Now you might be thinking, okay, if a t-test can compare 2 groups, well, why can't we just do a t-test on all possible combinations of groups? That's a great question. But the problem is that our alpha, that probability of a type 1 error, would accumulate. Remember, that's our probability of finding an innocent person guilty. We want to keep that as small as possible. So our alpha would accumulate, leading to what's called alpha inflation. And this occurs when we conduct several different tests on the same set of data. Too many tests spoil the data broth. Now, ANOVA evaluates all the mean differences simultaneously in just one test, regardless of the number of means. So it's simpler, and we avoid that problem of an inflated alpha level. Okay, now let's recall that the t-test was a ratio of a group difference for two groups divided by the sampling variability, where in this case, sampling variability is just the standard error. So whenever we calculated that t-statistic, it was equal to the difference between the groups in the numerator over the standard error in the denominator. Now, ANOVA is based on the same idea. We examine the variance among 3 or more group means, and then we compare that to the overall variance in our sample. We do this in a ratio that we call an F-test. Now, in fact, when we've got two groups, the F-test and the t-test give us the exact same results. So our new F statistic is going to be equal to the variance between our groups in the numerator divided by the overall variance in the denominator. Now, the F-test is actually named after the man who invented the idea. His name was Sir Ronald Fisher, and he was analyzing fertilizer data. The F in F-test began with fertilizer. Well, agricultural researchers had been trying to figure out which fertilizer worked the best by using a different one every year. Well, Fisher wanted a much better test. So he wanted to control for weather and land conditions. In fact, he designed experiments with multiple fertilizers in a single year. And then he assigned fertilizers to their plot locations based on a strictly random basis. So Fisher was getting data with far less noise. And the question became, how do we measure the degree to which the mean for the different fertilizer groups differed? Well, we needed to construct a sum of squared deviates measure for the 3 group means. Now, in fitting the ANOVA model, we more or less assume the same conditions as multiple linear regression. First, the observations within each sample have to be independent. Second, the population that we take the samples from has to be normally distributed and have roughly the same variability. Now, this is a big deal, right? If we violate that assumption of homogeneity of variance, well, it risks getting invalid test results. Third, the errors are independent, normally distributed, and have nearly constant variance. So Fisher sought to meet all 3 of these assumptions with the fertilizers that were assigned randomly and growing all the plants in the same field, the same year, with the same method. Now, if the assumptions are met, we perform an ANOVA to evaluate if the data provides strong enough evidence against the null hypothesis that all of our group means are equal. Well, what if you wanted to assess more than one input factor? Well, there are actually several different types of ANOVA. The one-way ANOVA, which we've been discussing so far, is an extension of the t-test to 3 or more samples. So we have a single factor divided into groups, such as types of fertilizer, and we want to look for the effect on a single continuous response variable, like agricultural output. Now, a one-factor ANOVA might be marital status, and we could break that factor up into never married, currently divorced, or widow. Or, for example, level of education, and then we could look at the effect on test scores. An example of a two-way ANOVA and higher, well, that looks at the contribution to the total variance of 2 input factors, like gender and marital status, or type of fertilizer and type of soil. So a two-way ANOVA compares levels of 2 factors for mean differences on a single continuous response variable, like comparing test scores by both level of education and race. Now, a 3-way ANOVA looks at 3 input factors. So gender, maybe marital status, and race. Or it could be type of fertilizer, type of soil, and type of irrigation. Now, you might hear another name that's commonly used for ANOVA, and that's Factorial Design. A 3-way Factorial Design is the same as a 3-way ANOVA. Now, we can sometimes look at the interaction of these input factors. So for example, the effective fertilizer type and irrigation method. So does the effective fertilizer change as the type or level of watering changes? Now here's how it works. Our null hypothesis is that the mean outcome is the same across every category. So mu1 is equal to mu2 is equal to mu k for all of our groups. The alternative is that the mean outcome is different for some or all of those groups. So in other words, there's at least one mean difference among the populations, where mu sub I represents the mean of the outcome for observations in category I. All right, here's the question. How many ways can the null hypothesis be wrong? Well, it could be that all of our means are different from every other mean. That's one way. Or it could be that some of the means are different from others, while some of them are actually similar. Well, remember our sample variance? S squared equals to the sum, as I goes from 1 to n, of xi minus x bar squared all over n minus 1. Now, the distance from any data point to the mean is what we defined as the deviation from this point to the mean. So xi minus x bar. Now the sum of squares is the sum of all of those squared deviations. So sum of squares is the sum as I goes from 1 to n of our deviations, xi minus x bar quantity squared. So here's how ANOVA works. ANOVA measures two sources of variation in the data, and then it's going to compare their relative sizes. So the first source is the variation between groups. For each data value, we're going to look at the difference between its group mean and the overall mean. We call this the sum of squares between. So this is the sum of squared deviations between each group mean and the overall mean, weighted by the sample size of each group, or n group. We solve for that as SSB is equal to the sum, as I goes from 1 to n, of our number of groups times the mean of the group minus the overall mean, quantity squared. Now the second part of our variance is the variation within the groups. So now for each data value, I'm going to look at the difference between that value and the mean of its group. That's called the sum of squares within. This is the sum of the squared deviations within each group. Here's how we solve for that. The sum of squares within is equal to the sum, as I goes from 1 to n, of xi minus xi bar squared. Now, if the group means are not very different, then the variation between them and the overall mean, the sum of squares between, it won't be that much more than the variation between the observations within a group, the sum of squares within. Lastly is the total sum of squares, or sum of squares total. Now this is the sum of the squared deviations between each observation and the overall group mean. Sum of squares total is the sum as I goes from 1 to n of xi minus x bar quantity squared. So in other words, the total sum of squares is equal to the within group sum of squares plus the between group sum of squares. Now, we assume the variance is approximately the same for each of our group's population. So first, we're going to combine the estimates of sigma squared across the groups, and we're going to use an overall estimate for the common population variance. Now, here's how we actually calculate that within group variation. We take our sum of squares within, and we divide by n minus k, where n is the total sample size, and k is our number of groups. This is equal to what we call the MSW. That literally means the mean square within. It's also called the within group mean square. Now, we can also look at the variation between groups, called the between group variation. This is equal to our sum of squares between divided by k minus 1, and we set that equal to MSB, which is our mean square between, where again, k is the number of groups minus 1. Now let's remember, what's our goal? We want to compare the sources of two variations, the mean square within and the mean square between. And so our test statistic, F, is going to be the ratio of those two things. So F is going to be equal to our between group variation, or MSB, divided by the within group variation, MSW. Now, if the null hypothesis is true, then F is going to be small. In fact, it's going to be close to 1, which means that, well, my between group variation is about the same as the within group variation. Right? In other words, the grouping doesn't explain much of the variation in the data. But now if the null hypothesis is not true, well, F will actually be large, which means that the between group variation explains a lot of the variation in the data, much more than the variance within the group. So in other words, the difference between the individual groups is much larger than the difference within each group. All right, so what we've just computed is called the F statistic, or the F ratio. Now, unlike our T statistic, which is based on sample means, this F ratio is a ratio of the sample variances. Now, the variance in the numerator measures the size of the differences among the sample means. And the variance in the denominator measures the other differences expected if the group means were not different from one another. Now, because these F ratios are computed from two variances, they're always going to be positive numbers. Okay, once we've got our F ratio, we can conduct an F test. This is the first time we've heard about an F test, so let's go through that a little bit slowly. The F test is designed to test if two population variances are equal. So it does this by comparing the ratio of the two variances. So if the variances are equal, well, the ratio of the variances will be close to 1. Now, if the variances are roughly equal, then the within group variation is the same as the between group variation. So grouping the data doesn't make a difference. The means from those groups are all going to be the same. Now, if the variances are unequal, then grouping has an effect. The between group variation becomes large compared to the within group variation, and our F ratio would be a lot greater than 1. So now the question is, how far does our between group variation need to get before we declare, hey, we've got different group means over here? So we actually need a distribution that only takes on positive values, right? Since our F ratio is always positive, and it's only going to reject the null hypothesis when we're larger than some threshold. So our solution is a sum of squared standard normal deviates, called the chi-square distribution. Now, in general, the chi-square distribution is obtained by taking the values of the ratio of the sample variance and the population variance multiplied by the degrees of freedom. So just like we use the normal distribution to test the difference in means, well, we could actually use the chi-square distribution if we wanted to test for a difference in variances. Well, the F distribution is formed by taking the ratio of two independent chi-square variables divided by their respective degrees of freedom. So, since F is formed by a chi-square, many of the chi-square properties are going to carry over to our new F distribution. First, the F values are all non-negative. Second, our distribution is non-symmetric. Third, the mean is approximately 1. And fourth, there are two independent degrees of freedom, one for the numerator and one for the denominator. Now again, the F distribution is any distribution that results by taking the quotient of two chi-square distributions divided by their respective degrees of freedom. Now, when we specify an F distribution, we have to state the two parameters that correspond to the degrees of freedom. First for the numerator, which is k minus 1, and then for the denominator, which is n minus k. Now here's a table of F values, and notice that it's organized by those 2 degrees of freedom. The degrees of freedom of the numerator are the between, which is shown in the table columns, and the degrees of freedom of the denominator are the within, which are shown in the table rows. For example, if the degrees of freedom of the numerator were, say, 20, and the degrees of freedom in the denominator were 19, then our critical value from the F distribution would be 2.1555. So we would compare our F ratio to this value, and we would reject the null hypothesis if our ratio were larger than 2.1555, or we'd fail to reject H naught if our ratio were smaller than 2.1555. Now, the ANOVA summary table is a concise method for presenting all of our ANOVA results. Check this out. In the first column, you see it lists the source of the variation, either between group or within group, followed by the total variation. The second column gives us the sum of squares. You see the sum of squares between, the sum of squares within, and then the sum of squares total. Now look at the third column. That's where your degrees of freedom are, k minus 1, n minus k, and if you add both of those, you get the total degrees of freedom, which is n minus 1. And that fourth column is the mean square, between group and within group. And then notice our F ratio is located in the last column. Now, how do we do ANOVA in R? Well, our first step in our analysis is to graphically compare the means of the variable of interest across groups. To do that, we're going to create side-by-side box plots of the measurements organized in groups using a function. Now, ANOVA requires that the variability of the groups be homogeneous, and we can observe the box plots to verify this assumption. Notice here, we require the package stats and graphics. And here we're going to do a box plot of weight on feed from, you guessed it, our chick weights data set. And here's the associated box plot. So ANOVA also requires the number of cases in your data groups to be approximately the same. Now in our case, our group sizes only range between 10 and 14. But what if we had larger variation in our sample size? Well, we could actually create what's called a variable width box plot. And this can show you whether your groups have the same number and shape. Now here, the width of the box plot represents the number in each group. And the height, as usual, shows you the spread of the data. In this example, our group sizes are 15, 80, 7, and 36. Now notice how the size of the box plot corresponds to the number of elements in each group. Now to test whether the difference in means is statistically significant, we can perform an analysis of variance, and we use the R function AOV. Now if the ANOVA test shows that there's a significant difference in means between the groups, then we might want to perform multiple comparisons between all pairwise means, just to determine which ones differ and how they differ. All right, once the ANOVA model is fit, we can look at the results using the summary function. And this produces the standard ANOVA table. Let's look at our code. We have results equal to AOV of weight tilde feed for our chick weights data. And let's do a summary of our results. Notice here we have our standard ANOVA table. We have feed and the residuals. We have the associated degrees of freedom, the sum of squares, the mean square error, and then notice our F statistic, 15.37. The p-value associated with that F statistic, super small, which gives us evidence to reject the null hypothesis that the means are equal. Now, studying the output of the ANOVA table, we see that that F statistic has an extremely low p-value. In fact, a p-value less than our alpha level of, say, 0.05 or 0.01 means that we automatically reject the null hypothesis of equal means between those 5 groups. Now, the Anova test answers the question whether there are significant differences in the K population means. But it doesn't give us any information about how they differ. And that's because Anova compares all the individual mean differences simultaneously in one test. Now, when we reject the null hypothesis, meaning we had a significant F ratio, we still have to figure out where are the differences. We know there's at least one difference in the means, but it doesn't tell us which means differ. So we have to do some additional follow-up tests to figure out exactly where the means are different. Now, a common multiple comparisons procedure is Tukey's method. This is named for John Tukey, an inventive mathematics professor with a joint appointment at Bell Labs. He was the first to use the term software and bit in computer science. And in 1970, he created box plots, the same box plots we've been using in this course. In fact, Tukey was a prolific inventor of methods. So we also call this Tukey's Honest Significant Test, sometimes abbreviated as HSD. Now, in Tukey's method, it's a single value that determines the minimum distance between treatment means that's necessary to claim statistical significance. A difference large enough that p is less than alpha experiment-wise. Now, this function in R, Tukey HSD, creates a set of confidence intervals on the differences between the means with the specified family-wise probability of coverage. The general form looks like this: Tukey HSD of x with a confidence interval equal to 0.95. Now here our x just refers to our fitted model object, for example, an Anova fit. And the confidence level is the confidence interval, in this case at an alpha of 0.05. Here are the results. So we've done our Anova of weight on feed, and now we're going to do a Tukey HSD on our results at a 95% confidence level. Notice here, we have the feed comparison, the difference, and the lower and upper ends of our confidence interval and an associated p-value. The first one compares horse bean to the casein feed. Notice that the difference between those two is negative 163.38. The lower confidence interval was minus 232.34, with an upper confidence interval of minus 94.41. That difference is significant with a p-value close to 0. Likewise, the second element in that result compares linseed to casein with a difference of minus 104.83 and also a statistically significant confidence interval from minus 170.58 to minus 39.07. Now notice the third one, meat meal with casein, has a difference of negative 46.67. The lower end of that confidence interval is minus 113.9. The upper end goes to 20.55. You'll notice that that confidence interval includes 0, and the p-value is not significant, saying that the difference in feed between meat meal and casing is not statistically significant. Now, Anova depends on the same assumptions as the least squares linear regression, only more so. In fact, let's go back to our opening example of 3 curves, but now with different variances for each. Now, could these 3 groups come from the same underlying population? Here's a possible pitfall. Now, don't be misled by the name Anova into expecting to analyze just any kind of variance. On the contrary, Anova assumes a shared variance, meaning roughly the same variance across all of the groups. Now, it's looking only at whether the means with that shared variance could also have come from the same distribution. Now, when the F-test shows that the means come from different distributions, then, well, that says, for example, the wonderful new fertilizer that you're testing gives statistically different results from other fertilizers. Well, much of the same way that we were able to extend simple linear regression to multiple linear regression, we'll see next time that we can extend ANOVA to multiple ANOVA. And we can also combine the features of regression and ANOVA to perform what we call analysis of covariance.